Okay, everyone, we're going to get started. It's 9 o'clock. It's unmuted yet. I want to thank everyone for taking time to come and join this climate change orientation seminar for Pacific Northwest region. My name is Levi Brecky. I'm the Chief of Research and Development in Denver. Today, myself and Kevin Werner, he's the NOAA Region Climate Service Director for Western Region. We're going to be giving you a three-part seminar. The purpose of the seminar is just to provide really high-level orientation on the climate change narrative, from the global change story down to local impacts, and then pivot in talk two to talk more specifically about how climate change relates to different mission areas within Reclamation, and I'll define what I mean by that in talk two. And then in talk three, it's going to be more about an opportunity. So what types of tools are available that folks can begin to apply in their respective mission areas. So that's a preview of the three talks. So the first talk is a Climate Change 101 talk by Kevin. Kevin joins us from his Seattle duty station. He's the NOAA Regional Climate Service Director for Western Region. Before his current position, where he's connecting climate science to application and decision makers in the Western U.S., Kevin has worked with other parts of NOAA, including the National Weather Service and also the Colorado Basin River Forecast Center in Salt Lake City. So he's very familiar with reclamation operations from his CBRFC days. We're very excited to have Kevin. And Kevin, can you hear us?
Yeah, thanks, Levi.
Okay, let me change presenter over to you. And you can take it away.
Great, thanks, Levi. Thanks for the introduction, and it's good to be here. Let me just check and make sure people can hear my voice and see my screen.
Yes, we can hear you and see your screen.
Excellent. Thanks, Levi. So this talk was developed in collaboration with Dave Easterling at the National Center for Environmental Information, formerly the National Climate Data Center, or NCDC, along with Paul Miller, who's a hydrologist at the Colorado Basin River Forecast Center. So we've been sort of tag teaming these talks around the region, and I get the privilege of talking to you folks today. So as Levi said, this is going to be sort of a Climate Change 101 talk. We're going to focus mostly on the science, the high-level science behind climate change, and then its impact on Western U.S. watersheds. So to start out with, just wanted to sort of define what we're talking about when we're talking about weather versus climate. So weather is, as you can see on the screen, is local and short-term. It changes day to day, hour to hour. Whereas climate is like weather, but on a longer time scale, year to year, decade to decade. So this slide's from Dave Easterling, and he has this clever little thing in the middle that climate tells you what clothes to buy and have in your wardrobe, whereas weather tells you what to wear each day. So this talk is focusing on climate rather than weather. So I wanted to start out with a little bit on the greenhouse effect, but we'll get more into this as we go along. But wanted to start out with the idea that the greenhouse effect is a natural phenomenon. It's important. If it wasn't for the greenhouse effect, the Earth's temperature at the surface of the Earth would be about 0 degrees Fahrenheit, rather than what we observe, which is closer to 58 degrees Fahrenheit. And so what is the greenhouse effect? There's radiation that comes from the sun. We call it shortwave radiation. This is what, among other sort of wavelengths, what you see, what visible light you see from the sun. And so that radiation comes in to the Earth's atmosphere. Some of it's reflected off of clouds or land surface, especially snow-covered or ice-covered land. But a lot of that, most of that radiation makes it through to the Earth's surface and is absorbed by the Earth. And that's responsible for warming the Earth's surface temperature. Because the Earth is much colder than the sun, it emits a much longer wavelength of radiation called infrared radiation. So that's emitted by the Earth's surface back out to the atmosphere and eventually to space. It turns out a much larger percentage of that radiation is absorbed by the atmosphere and re-emitted back down to the Earth's surface. So that difference in radiation, there's more of the long-wave radiation is being sort of redirected back to the Earth than the short-wave radiation from the sun is being redirected back to space. That difference is the greenhouse effect. and that's responsible for this difference in temperature between what we would have without an atmosphere and what we have with the atmosphere. So with that in mind, wanted to show the temperature record. So this is a time series of annual temperatures, annual average temperatures across the entire globe, going back to 1880 on the left, and extending out to 2014 last year on the right. So the horizontal line is the long-term average, and then the bars are showing the difference from the average. So you can see the last part of the 19th century and the first part of the 20th century, every year was below average. In the 1930s and early 40s, we had a few years, with several years that were above average, then below average, above average, and then since about the late 1970s, every single year has been above the long-term average. And in particular, the dark red years on the right, those are the 10 warmest years on record, and you can see they've all happened in the last 15 years. So there's a pretty obvious trend in this data set. I should say, pragmatically, if you have questions or comments as we're going through this, feel free to interrupt, and we can take those as we go through. So this table is just looking at those 10 warmest years. When did they occur, and how much above average were they? So the warmest year on record was last year, 2014. The anomaly was 1.24 degrees Fahrenheit or 0.69 degrees Celsius. Kind of keep that 1.24 number in mind as we go through this. The next warmest years, there was a tie between 2010 and 2005. You can see 1.17 was the anomaly for both of those years. So quite a big difference if you look at the difference between the warmest year and then the next two warmest years relative to the years below them. 0.07 degrees Fahrenheit, which is, doesn't seem like a lot in the weather context, but again, thinking climate context, that's actually quite a large number. And the difference between the warmest year and the next warmest year is much greater than any of the other years on this table. So this suggests that perhaps we're seeing an acceleration in the trend, at least with 2014. So what I've showed you so far has just been global average temperatures. Of course, we're interested in the distribution of those around the globe. We all live in a certain place, and nobody lives in the global mean. So what did 2014 look like in terms of its temperature anomalies? This chart is showing the temperature anomalies in grid cells across the globe. So the darkest red color indicating grid cells that have experienced their warmest temperature on record. And then the other red colors are indicating places that were above average, but not the warmest year on record. The blue places are places that were below average. So in the left, you can see California experienced its warmest year on record, and that shows that pretty clearly here. There was also a very large swath of the northeastern Pacific Ocean just south of Alaska that was quite warm. So that was 2014. This next chart goes back to the global average temperatures. This is just the same thing I showed a couple slides ago, but looking at it by decades. So we're looking at the decades of the 1880s on the left, all the way up to the decade that started in the year 2000 on the right. And here you see a very pronounced increase in temperatures over the entire 20th century and extending into the first part of the 21st century. Okay, so this begs the question, why is it warming? And there's several possible reasons we list here. One is the sun. Perhaps the sun is changing the amount of energy it's emitting, and we're receiving more energy from the sun. The second reason would be perhaps the Earth itself is emitting additional energy, and that would be in the form of volcanoes, which are basically a vehicle by which the Earth's energy can be emitted from inside the Earth to the atmosphere. Maybe it's part of, you hear this next one a lot in the popular media, maybe it's part of longer-term variability. Maybe there's some kind of natural phenomenon that's responsible for the temperature increases we've seen. And then the last reason, possible reason, is maybe it's stuff in the atmosphere. So I'm going to talk about all of these. I'm going to start with the first three. So this chart shows the temperature impacts globally from those first three things I talked about. So The order is a little bit different. The top order is looking at El Nino, La Nina. This is the largest source of natural variability we see in the Earth's global mean temperature. And so this chart goes from 1980 through 2010. You can see the large El Nino event we had in the 1982-83. You can see another one in 1998. And we're perhaps headed for another one this year, which obviously doesn't show up here. So these El Nino events are responsible for variations on the order of 0.4 to 0.7 degrees Fahrenheit. And you don't see a trend in this chart. There's a lot of variability, but not a trend. So recall the observed difference we've seen in 2014 was 1.24 degrees Fahrenheit. So something about double, maybe a little bit more than what we've seen from El Nino. The next chart shows the temperature impact from volcanoes. So we've had a couple of major volcanoes, Mount Pinatubo, I think in 1991, and I don't know which one the one was in the 1980s. But these are responsible for decreasing the Earth's decreasing the global mean temperature. As you put stuff in the atmosphere, particulate matter, if it gets up into the stratosphere, it can last for a year or two. It can cause more shortwave radiation to be reflected back to space. So it can actually have a cooling effect. Actually, does have a cooling effect on the Earth's temperature, but it's fairly short-lived. And from these major volcanoes we've seen, it typically lasts for a year or two, and they're relatively few and far between. So again, there's no particular trend. If we look back in the longer time series, we don't see a trend in this either. And so the final one on this slide is the solar activity. Is the sun growing warmer, or is there more energy coming from the sun? And in fact, there is a cycle in the sun's energy. We see this 11-year cycle with sunspots that increase and decrease. And there is, in fact, some impact, some fairly minimal impact on the Earth's temperature on the range of 0.1 degrees Fahrenheit to 0.2 degrees Fahrenheit. So again, much less than what we've observed in 2014, and again, no trend. So we can, I think, based on this slide, sort of dismiss these three things. Let me just talk a little bit more about the sun's energy output. This is a similar chart on the bottom showing the sun's energy output. You see that 11-year cycle. And on the top, we've added now the observed global surface temperatures in blue. And you see the trend that we talked about before. And you can see that these two things are really not related to each other. So the one thing we haven't talked about is the stuff in the atmosphere. So when we're talking about stuff, we're largely talking about greenhouse gases, carbon being the dominant one. And here we know, based on what we've been doing since the Industrial Revolution, we know that we're putting more carbon in the atmosphere than was there previously. So this is a chart showing carbon emissions from fossil fuels and from land use change going back to 1000 AD and extending to into the 21st century. The Industrial Revolution is highlighted, so you can see that the fossil fuel carbon emissions really started during the Industrial Revolution and have really accelerated since then. So if we look at that in the longer range, this goes back to 800,000 years ago. You can see and this is plotting carbon dioxide concentration. So we can get carbon dioxide measurements from the distant past through ice cores, little air bubbles and ice cores. We can also get them from coral reef samples in the tropics. So based on those sources of data, we're able to tell what the CO2 concentration was, carbon dioxide concentration was in the atmosphere going back into the distant past. And we do see some cycles in that carbon dioxide concentration. Those long cycles are due to fluctuations in the Earth's orbit. However, we don't see anything going back to almost 1 million years ago that is anywhere near what we're observing now. So we're coming up on 400 parts per million in terms of carbon dioxide concentration in the atmosphere. You can see that exceeds anything in the distant past. It's not just carbon dioxide. Methane, nitrous oxide are also are also greenhouse gases. So the chart on the upper left is the carbon dioxide. This is actually measured now in the atmosphere. We have a pretty robust measurement of carbon dioxide going back to the 1950s. And you can see there's an annual cycle in carbon dioxide, but there is this very apparent upward trend in carbon dioxide. Similar story for methane and for nitrous oxide. So all three of these important greenhouse gases are increasing, and they're increasing because of the industrial activity that people are responsible for. So this next slide starts to relate carbon dioxide. It does relate carbon dioxide to temperature. So this is on the left side is the same chart that I showed earlier, but now I've superimposed the carbon dioxide concentration curve on top of it. And so you can really see that these two curves are pretty well related to each other. When there's increasing CO2, we observed increasing temperature. Sure, there's other things going on. There's variability underneath that, or underneath the temperature signal, especially on a year-to-year or even decadal. But in the longer time scale, we see this pretty strong correlation between, in this case, CO2 concentration, but more broadly, greenhouse gas concentration and temperatures. On the right this is a sort of modeling exercise that was part of the IPCC, or Intergovernmental Panel on Climate Change assessment, where they modeled the Earth's atmosphere both with and without the anthropogenic industrial effects of increasing greenhouse gases. So the with is the pink band, and then the without is the blue band. And then on top of that, we superimposed the observed temperature. So up until about the 1960s and 70s, these two curves were pretty similar to each other, and it wasn't very clear based on this kind of analysis that the human effects on the greenhouse gases were really driving the temperature profile. But since about the 1970s, there's been a very clear separation between these two different sets of model runs, with the observed temperatures clearly tracking inside the model runs that include the greenhouse gas effects from human activity.
Hey, Kevin.
Please.
On the slide you have here on the right chart, on the black observed line, there was a question from our Upper Colorado region about the 1940s. Is there any explanation of why the temperature kind of increased around that decade and then fell off?
Right, good question. I could speculate. I know there's been research on this. I'm not up on it, so I think maybe we should probably hold that question and get back to it. Sounds good.
Can I ask a simple question on that? Is there like a mental model besides these fancy computer models that could, why does CO2 make it warmer?
Did you hear the question, Kevin? Why?
It was a little muffled. Something about CO2 making it warmer.
What's the physical link between increased carbon dioxide concentration or other greenhouse gas concentrations and the global temperature getting warmer?
Oh, good question. So recall back to, well, let me just go jump back real quick to this slide on the greenhouse gas at the beginning. So essentially the changing greenhouse gases such as carbon dioxide increases the greenhouse effect. So there's a natural greenhouse effect plus this greenhouse effect that we're adding through our industrial activities. So if we increase that greenhouse effect, we increase the surface temperature of the Earth. Does that answer the question?
And also at the gas molecular level, they can physically prove how it emits long-wave radiation when it gets excited. So they're accumulating a bunch of physical information on the different gas types, and then as the concentration of those gas types increase, it just kind of increases the blanket, the insulation.
But when you say greenhouse, that's what it is.
That's essentially it, yeah.
Okay, thank you.
Yeah, thanks, Levi. Okay. Where were we? Okay, so jumping back to the slide deck, any other questions on this slide? Okay, moving along. Of course, there's more to climate change than temperature. So far, we've just talked about temperature, but obviously you all are interested in the hydrologic cycle and especially surface water. So why do these temperature impacts or temperature changes I've been talking about, why do they matter for hydrology? And they matter for a lot of reasons. So this is just a chart that shows the sign, the increase or decrease for different elements of the hydrologic cycle. So we talked about the surface temperature over land and over the ocean increasing, and over that drives an increase in water vapor in the atmosphere. As the atmosphere warms, it's able to hold more water. It also drives temperature increases, obviously, in different places in the atmosphere. And so that, in turn, decreases the glaciers, decreases snow cover, sea level increases, sea ice decreases, ocean heat increases. So all of these things have impacts, obviously, on the hydrology, which you all care about. So let's get into that a little bit more. This is just a couple of pictures from the Muir Glacier in Alaska. This isn't unique to Alaska or the Muir Glacier. We've seen pretty much glaciers everywhere around the world receding, and receding fairly dramatically when you see the photographic evidence of this. In this particular case, this glacier has retreated more than 7 miles, then by more than 875 yards. So obviously that has a huge impact locally. It turns out it also has an impact globally as we have less and less area covered by snow and ice and glaciers. So I wanted to introduce the third National Climate Assessment. This is a assessment of the state of the science, essentially. This was National Climate Assessments have been conducted since 1989 under the auspices of the U.S. Global Change Research Program. So this is a federal effort that was established by the first Bush administration and then made into law by Congress in 1991, I believe. And it mandated that there be these national climate assessments every 4 or 5 years. Of course, we haven't maintained that frequency. This is only the third one. But nonetheless, it's a very comprehensive assessment. It's conducted across many agencies and includes a lot of input from academia and from other sources. And so its main message is that climate change is happening now. We're feeling the effects now, and there's important opportunities to manage and prepare. There's also there's a lot of resources associated with this climate assessment that I'll talk about at the end in terms of how you can access them. So again, the climate change is changing, and it appears it's apparent across the U.S. in a wide range of observations. Global warming of the past 50 years is primarily due to human activities and predominantly the burning of fossil fuels. So we've talked about most of that. We've also talked about temperature changes globally. This is looking at temperature changes in each one of the regions defined by the National Climate Assessment. So you can see there's 10 regions. You can see they're spelled out here. The one that's obviously most interesting to you all is the Northwest here in the upper left below Alaska. And you can see a similar temperature increase or trend as we saw globally. It's obviously somewhat different. Looks like there was a pretty warm decade in the 1920s or 30s. But we still see the last couple decades as the two warmest in that record. So precipitation is obviously important. This is looking at the observed precipitation changes in the same regions. So for the Northwest, there's been a bit of an upward trend, but not so much since the middle of the 20th century. It's been more constant. And then also, I think it's important with precipitation to point out that we don't know nearly as much about precipitation as we do about temperature. The signals are not really strong. And you can see that within the Northwest region or other regions. You see a lot of heterogeneity in this chart that you didn't see in the chart with temperature. So you see places where there's less precipitation, places where there's more precipitation. And frankly, there's a lot of noise in that. Extreme weather, this is another thing the assessment looked at is, are we seeing trends in heavy precipitation events, which they define to be in the upper part of the distribution of the precipitation events on, say, a 1 hour time scale or something like that. I don't know the specifics. are we seeing increases or decreases in that part of the extreme precipitation events? So this is looking nationally across the U.S. We do see an increase in extreme or heavy precipitation events. We look at that by National Climate Assessment region. We see increases just about everywhere except for Hawaii. But in the West, those increases are not as dramatic as they are in the East.
Hey, Kevin. On this slide here, this is Levi again. Just to clarify again, this is change in frequency, but not change in intensity. Correct?
That's right.
So we don't.
That's right.
Go ahead. Do we have similar information on change in intensity, or is that more uncertain?
We do. I mean, both questions sort of they require a definition of what is a heavy precipitation event, right? And typically, again, I don't know exactly what the duration they're looking at is here, but typically they're very short durations that they look at in these kind of studies. So they're like 1 hour, whereas you all are likely interested in sort of longer duration, like a day or even a month or something like that. So I would just say for both questions, both the frequency and the amount, you need to be pretty careful about what thresholds you're choosing. And certainly, those studies are possible, and many of them exist already.
Sure, that makes sense.
Anybody else on this slide?
Go ahead. Thank you.
Okay. Thanks, Levi. Okay, so everything we've talked about up to this point has been observed changes. We've been looking at observed data, 20th century data mostly, but obviously we're interested in what's going to happen in the future. So what do we know about that? We know that the human activities that are responsible for emitting greenhouse gases are increasing across the world, and that's going to have an impact on the climate. What does that impact look like? So these are two different projections or two different futures of looking at temperature changes. So when we're doing these future outlooks, we define scenarios for greenhouse gas emissions in the future. We're basically making an assumption about, are we going to continue burning greenhouse gases at similar rates to we've seen in the past, or are those going to continue to increase, are they going to decrease? And then we run climate models forward in time accordingly, so we can use kind of the similar models I talked about earlier for the 20th century. We use those same models to project forward through the 21st century. So on the left is one of the lower emission scenarios run out through, I believe this is through the end of the 21st century, so we're looking at the year 2100, I'm pretty sure here. And this is the lower emission scenario, or B1 on the left. And you can see we're going to see temperature changes in this scenario of 3, 4, up to 5 degrees Fahrenheit in the lower 48 Alaska. The Arctic is going to warm much more. But if you think about 2014, remember the number 1.24 degrees Fahrenheit was the anomaly for 2014. So we're looking at numbers that are 2, 3, 4 times that in the lower emission scenario. In the higher emission scenario, the 8.2, this is just one of the higher emission scenarios. We see a much different future. Here we see temperature increases of 6, 7, 8, 9, 10 degrees degrees Fahrenheit. So several times more than the increase we saw in 2014. So pretty different futures depending upon the emission scenario is kind of the bottom line for this chart. So we look at that higher emission scenario, A2, and we look at its projected changes in precipitation for just winter season, just cool season precipitation or winter precipitation. We get this chart. So the green colors are indicating places where we'll see increased precipitation, and then the warmer colors, I guess it's orange, yellow, those colors are places we'll see less precipitation. And then the hatching, the striping lines, those are indicating places where we have more confidence in the projection than in places where there's no hatching. So what you see here is a pretty dramatic increase in precipitation the further you go north, and then places further south, places that are already dry, become drier. And There's a couple of reasons for this. One, I talked about already, the atmosphere, as it warms, it's able to hold more moisture. So there's more precipitation associated with that increased moisture in the atmosphere globally. But we also see, if you look at the model runs in detail, you see a gradual northward shift in the jet stream. So you see storms sort of increasingly favoring the northern latitudes over the southern latitudes, at least in the mid-latitudes where we live. So another area that I haven't talked about much to this point is sea level. We've already observed increases in sea level. This is a chart that starts in 1800 and goes through 2100, so it includes our observed sea level data from proxy records and tide gauge data and satellite data. You can see that we're becoming increasingly more precise with our sea level measurements as we have increased the capabilities of the observing system. And we also see a small but pretty steady increase in sea level rise on the order of, it looks like coming up on 7/10 of a foot now. In the future, we see a lot more uncertainty in those projections, but continuing and increasing increases in sea level rise. The uncertainty associated with this is related to the uncertainty in the temperature, but it's also very directly related to the uncertainty about when we'll see large melt-offs in Greenland and Antarctica, especially Greenland. So these increases are due to kind of two things. One is melting snow and ice over land, primarily Greenland and Antarctica, and then two is just a thermal expansion of the water itself as it becomes warmer. And it's about half and half between those two effects. And of course, to bring this home to you all, what you're interested in is water, right? So this is on the bottom. This is a study that looked at projected changes in water withdrawal. So on the left is without climate change, and on the right is with climate change. So they're obviously making a lot of assumptions in the study, but nonetheless, it's an interesting sort of comparison of what a future with a climate change looks like in terms of water withdrawals versus what a future looks like without the climate change. So in the Northwest, you see significantly more water withdrawals across the entire region to places that are already expected to see increases in water withdrawals, such as the central part of Idaho, are expecting to see even more in a changed climate. Plant hardiness, this is another measure. I'm not an expert in plants at all, so somebody please correct me if I get this wrong, but the folks that are experts in plants have defined these hardiness zones based on an algorithm that includes pretty heavy reliance on temperature. So as the climate changes, these zones move northward, generally speaking, northward and upward in elevation. So over the past 10 years, we've been able to look at where these zones have changed, and you can see they have been changing, moving to the north and upward in the west, where we have pretty significant elevation profiles. But over the next 30 years, we're expecting to see even more dramatic changes in these plant hardiness zones. So when we drill down to the specific regions, the National Climate Assessment has, like I said, these 10 regions. So the three that are most of interest for reclamation are the Northwest, Southwest, and Great Plains, and in your guys' case, the Northwest. So for each one of these regions, the climate assessments define 4 or 5 key messages. And there's a chapter in the climate assessment that goes into each one of these regions in more detail, and each one of these key messages in more detail. So these are messages that are sort of roughly ordered in order of importance. And so for the Northwest, it's water-related challenges is the number 1, coastal vulnerabilities is 2, impacts on forests is 3, and agriculture is 4. Southwest, you can see the water is number 1, and the Great Plains water is also number 1. So that, I think, is telling and important for what you all do. Agriculture, which is obviously closely linked to water, is on the list for all 3 regions as well. So I already showed this chart. wanted to talk a little bit about what does it mean for water. And so in the Northwest, this is a chart from the National Climate Assessment showing a number of the key river gauges around the region, and we're looking at changes in the hydrograph, the mean hydrograph. So on the left is just a sort of random stream gauge. I'm not sure which one is the black is the historical hydrograph, and then we're looking at three different points in the future. So the blue line is the 2020s, the orange line or yellow line is the 2040s, and the red line is the 2080s. And each one of these are assuming the A1B emission scenario. So it's one of the higher but not super high emission scenarios. And so what we see is a sort of gradual change from a snowmelt dominated basin with the largest peak in the spring, late spring months, early summer months, to something that's more rainfall dominated basin with a more broad and more broad peak, but over the winter season. So it's not that there isn't a peak in the winter season now. There is. Typically, we see this in a lot of places in the Northwest, a peak in November, December, before things get really cold. We do have rain events in a lot of the basins, especially in the Cascades. But we're seeing a very significant increase in that winter peak and then a reduction in the summer peak, the spring-summer peak. So the map on the right is focusing on that summer stream flow. So obviously this is important for a lot of the work you all do in terms of maintaining flow targets for various things. And what we're seeing is a real mixed message, but in general, most of these stream gauges we're expecting by the 2040s to see lower stream flows in the summertime. Just one comment on the sort of heterogeneity of these gauges. That's due in large part to the different elevation profiles of the basins. And I realize I'm talking to people that know this quite well, but basins that are really high in elevation are likely to see maybe less changes in the basins that have a lot of elevation in the mid areas, and then basins that don't really have high elevation or don't really have high terrain at all, such as in central or eastern Washington or maybe down in eastern Oregon. Those places don't currently rely on snowpack or snowmelt, so they're not going to see as much change as places that do rely on snowmelt currently. This isn't maybe as much interest to you all, but in the Southwest, the storyline is similar. They're expecting to see less precipitation, but they also see this declining snowpack. So this is looking at snow water equivalent changes over the similar time frame. So the red bar is the average snow water equivalent for each one of these states, each one of these 6 states in the 1971 to 2000 time frame. And then the gradually lighter bars reflect what are we going to see in terms of peak snow water equivalent, or I think it's probably April 1 snow water equivalent going forward in time, the percentage of that 1971 to 2000 period. And you can see for all 6 of these states, we're seeing decreases, and then particularly for the southern states, those decreases are more extreme. This is not a national climate assessment. This is a study that we did in Salt Lake City, looking at a fairly small basin there, Big Cottonwood Creek, and looking at similar changes in the hydrology based on sort of hypothetical increases in temperature of 3, 5, 8, and 10 degrees Fahrenheit. This is a study that Tim Bardsley ran using the River Forecast Center model. And you see a similar result to what I showed before, only this one doesn't really transition to a rain-dominated system. It just melts earlier and earlier. This is a very high elevation basin. So I wanted to include this just to kind of hammer home the point that there is a lot of heterogeneity or differences between basins based on their elevation profile and their current hydrology. So this is a concluding thoughts slide that Dave and Paul and I came up with. As the impacts of climate change continue to be realized, resource managers such as yourselves need to be proactive, innovative, and open to making changes. Communication and collaboration are essential. I think we need to be more and more integrated across disciplines, as we've try to tackle this problem. It's increasingly difficult to do that within the traditional discipline of stovepipes, and we need to start doing this now. So even if this is all a big hoax, there's still a lot of reasons to move forward for this kind of a funny chart. And I wanted to wrap up with just a few resources. So I mentioned the National Climate Assessment. It's available online. It has a pretty snazzy website. It's very approachable by just about anybody. So I'd encourage you to go take a look at, especially the chapter for your region. There's also resources here in NOAA. We've got me. We've got River Forecast Centers, Northwest River Forecast Center for you all. We've got the Regional Integrated Climate Assessments. So there's one at Oregon State led by Phil Mote called the Climate Impacts Research Consortium, which is a great resource for the Northwest. There's regional climate centers. There's a Western Region Climate Center in Reno, Nevada. Each state has a state climatologist that have sort of varying degrees of capability and capacity for help providing technical assistance and that sort of thing. Within your department, within DOI, there's the landscape conservation co-ops and the climate science centers that I suspect several of you are plugged into. The USDA is spinning up the ag hubs, and there's a lot more. So it's a fairly complicated landscape out there, but there's a lot of resources that are available to folks like you. So I've been talking about how cool the National Climate Assessment website is. This is a screenshot from it. So if you go there, you can look at the full report, but you can also look at the highlights. And there's a lot of, most of the charts and figures I showed in this talk are in there. There's also a lot more pretty pictures and things that can be useful in helping communicate to your stakeholders, and as well as helping you sort of spin up on the science of climate change and the impacts. Lastly, there's this Climate Change Resilience Toolkit, which is an initiative of the Obama administration, leveraging a lot of the stuff from the National Climate Assessment into tools that are pretty easy to use. This is still something under development, so if you do use this and want to see changes or want to see something that's not there, there's an appetite to build those things in. So here's my contact information, and I'm happy to answer questions or
we have plenty of time for questions. So, and as people are thinking about questions, I'll offer up that we're going to make these slides available to folks after the seminar. I know some people were taking notes, trying to write down websites, and we didn't really I should have given you that heads up earlier on. Also, we're capturing this presentation. The PN region's capturing this presentation on video, so that'll also be available to folks who can attend today. And lastly, we'll also distribute a summary that includes summaries from the 3 talks, very, very brief, and includes some key links. So are there any questions?
I have a question. I've seen the graph of temperature increase in CO2 concentrations over time before, and they're usually just laid over each other. Has there been, you guys know of any R squared or some sort of correlation that's been done, or know what that number is?
Kevin, you want to go ahead?
I know people have looked at that pretty extensively. I don't know the number off the top of my head. Do you, Levi?
No, I'm not even aware of statistical, like studies that just publish those stats. Usually what I'm used to seeing presented is the chain of events or the conceptual links. So like the gases themselves have these characteristics of absorbing radiation and giving it off, and then there's the observed concentrations, the observed temperature trends, and then the climate model simulations. But I haven't seen, that's a good question, I haven't seen people try to give it a correlation or whatnot. I have seen some questions about the long-term paleo record and some apparent out-of-sync qualities on long-term temperature and carbon dioxide. For the most part, there's good evidence that they correlate, but there are some wrinkles, and there's still science activities going on to understand that. But in the recent industrial revolution era, the correlation is striking.
So I have a question, Levi. That And I know it was presented earlier about that link. I noticed through some of the graphs from the 1930s to 1940s, there seemed to be one of those kind of anomalies. That would be really interesting to find out if you or Kevin have some information on that you could send out with the summary.
Yeah, well,
Because that was just interesting. It was one peak, and then it went back to more of a typical trend.
and the thing is, it's a global peak, which is kind of a curiosity. If it was just a U.S. peak, then maybe it had to do with the Dust Bowl or something like that. But and Kevin and I can see if there is any information. There might not be.
If there are any questions from the remote areas, there's a raise your hand function and go to webinar, and then we can unmute you one at a time.
Or if you just like to chat your question in the chat window, we can repeat it for you as well.
I'll ask another one. Is that okay if I ask another one?
Go for it.
My question is kind of about the kind of a big mass balance, evaporation and precip.
Mm-hmm.
Is there still the same amount of evaporation and precip, and it's just spread over different, or is there any change like in that? Whether measured data or model data, what, do we know that?
Kevin, do you want to take a first crack?
Sure, you can back me up. I mean, folks have looked at, NASA in particular, have looked at water balance, like you're talking about. There have been changes. Are you asking about globally or regionally, or
just kind of globally? You know, what's the mass balance doing?
Global.
Global, right? So with the satellite error, I mean, obviously we're able to measure some aspects of the water cycle in ways that we weren't before, and so there have been efforts at looking at the global water balance, and I'm not super up to speed on the results there, but my sense is that there are changes. You know more about that, or?
I don't know more specifics, but I can add a couple sideboards. So the warmer the atmosphere, the more moisture it can hold. So a warmer air can hold more moisture. Now, does it? It depends on the cloud activity. So you're right that globally precipitation will balance evaporation. It has to, because we're not losing water to space. But the question of whether the rate of evaporation is increasing as the atmosphere warms. Not sure about the rate, but the amount. There is evidence that there is increasing humidity in the atmosphere, increasing moisture in the atmosphere, and we could even. There may be some information in the National Climate Assessment that speaks directly to that point. I would suggest checking that out. But
it'd be kind of interesting too. Notice the precip on land overall change.
Well, then there's the distribution, and as you saw in Kevin's modeled precipitation chart for North America, the story is that the wetter areas tend to get wetter in the future, and the drier areas tend to get drier. And the models for the wetter areas up north in Canada, they're reflecting that first notion that warmer air can hold more moisture. So the storms that normally track to the north, they're laced with more moisture, they dump more rain. That bullseye of drier towards Mexico and over Mexico, that has to do with how the models all kind of agree that the tropical circulation from the equator up to the desert belts, like the Sahara, the American Southwest, other desert regions of the world, that circulation is changing in the models and pretty consistently across the models, that it's kind of fattening and the intensifying the atmospheric subsidence that causes the deserts. But that's maybe getting a little off track of your question.
I'd just add on evaporation. Evaporation is not a function just of temperature alone. So, I mean, wind speed is a key factor. And there's been regionally some studies that have suggested, some places there's a stilling, and some places there's an increase in wind, and that has that can have a pretty dramatic impact on evaporation. Does have a dramatic impact on evaporation regionally. I'm not sure that I haven't seen much globally. Not to say there isn't on that.
Great question. You stumped us. Are there any?
I have a question. Is there a place where I could find information about some of the models you guys used and maybe how calibration and also validation was performed and how well it worked?
So I'll take a crack, Kevin, and you can fill in where I missed.
Your areas, you like that.
The first part, you can go to that National Climate Assessment. They have a whole chapter on global climate models in the most recent crop. On your second part of your question, are you a hydrologist by chance?
Yeah. A little bit of
So,
calibration.
yeah, no, it's so common in the water resources world, especially amongst hydrologists and water resources engineers. We're used to working in a basin setting, and especially with hydrology models, we do this thing where we match how the model simulates runoff to past observations of runoff, given past observations of weather. And that process is called calibration. With the global climate models, they don't do that kind of exercise. They do, the climate scientists will call it tuning, and they'll tune some features in the atmosphere, one thing they call optical depth, which is basically something describing the blanket, the radiation blanket quality of the atmosphere. And that's tuned to kind of get the global energy balance right. But then how the global model simulates ocean circulation, atmospheric circulation, ice dynamics at the poles, land cover, vegetation dynamics. There's a lot of moving pieces. And no, there's no calibration and validation. But there are verification studies, but just not done the same way.
There's a lot more factors than a stream gauge, obviously.
Yeah,
because there's all those other moving parts. But yeah, I was just kind of curious on how you even get to.
I'm giving you an explanation, not an excuse. I mean, we would like the global climate models to be more finely tuned and developed in ways that are recognizable to us as engineers, but they have kind of a different world.
It's part of the reason why we don't get so many models, right? Because we don't. None
Yes.
of them are really particularly believable.
Yes, that's a good, very good point.
I would just add one little thing. I mean, the goal with the global models is largely to look at changes rather than the actual absolute values. So some in the community would argue that we want to, we're more interested in the changes from, say, the 20th century to 21st century than we are in the absolute values that the model is suggesting for either one. And so that's,
so how
again, not making an excuse, but.
So we're interested in how the weather patterns respond to a change in greenhouse gases, for example.
Right.
We have another question there.
Hi, Levi. Lisa Stark. I don't know how to frame my question, but I'm interested in understanding how climate change might affect ocean conditions. And so, I know we didn't cover it today, but is there a place to go and look for that information to see if there's some predictions on what ocean conditions might occur based on climate change?
Kevin, why don't you go ahead?
I couldn't. You said ocean conditions?
So the question is impacts. Where can folks here find information about changes in ocean condition? I'm guessing you're thinking with respect to anadromous fish,
Yeah.
salmon.
Okay, absolutely. There's, I think there's a chapter on oceans in the National Climate Assessment. I could be wrong, but there's the models that we're showing here. I mean, they include an ocean component. There's been a lot of research on the connection to fisheries in particular. I can, if you have specific questions, I can help you get connected with some of the folks that are looking at those issues in the National Marine Fisheries Service Science Centers.
And what
I can
about
also follow up? Go ahead, Levi. Sorry.
Oh, yeah, and your last slide of region resources? Do any of those groups have folks that are studying ocean conditions? Wondering maybe the RISAs or the Climate Science Center?
Actually, for the Landscape Conservation Cooperatives, the North Pacific is actually doing quite a bit of science related to it in terms of the sea level rise, the salinity, how it impacts the vegetation and the habitat, and how the habitat actually, species are migrating in response to some of the projected rises in sea level.
So is there more coastal vulnerability, coastal
Absolutely,
shelf
yeah.
resources? And then as far as open ocean, like any work on acidification or
I don't think
temperatures?
I don't know if they've gone quite out to open ocean, but they're looking more at the coastal estuary areas. That's kind of been the big focus, and it's that connectivity to the freshwater,
Sure.
which is the estuary work primarily.
The NOAA Fisheries Science Centers are doing directed research on ocean acidification and circulation patterns, and then impacts directly to critters and laboratory tests and those sorts of things. But I think they're all available through NOAA Fisheries. I was just looking it up because I couldn't remember the exact website. But yeah, there's a NOAA Fisheries climate science site. They just released their strategy, about 9-10 months ago as well. And
Any other questions from the web? I think we have one. It's for Matt Kelsch. Matt Kelsch. He's listening in from UCAR Comet in Boulder, Colorado. Comet is a group that's helping to capture our seminar content, and we're going to make an online self-paced learning module for later use. And Matt writes that the climate assessment has chapters on ocean acidification and sea level rise. So another reason to check out that National Climate Assessment. Thanks, Matt.
Thanks, Matt.
We should have read the chat box before we started to blather. Okay, well, I want to thank Kevin again for that great first talk.